Hello. I'm back. Hello, guys. So, today I will be starting with where I left yesterday. And before doing any of that, let's recap for a while because I hope you people might like. I'm sure you guys are very smart, but still, like revising few things couple of times are not a bad idea. So, anyway, yesterday we started our study with CMM and we studied the basics of it. Basics as in what is this machine, does it do, then what are different type of shapes. In shapes we studied three types of things, which was actual, nominal, and substitute. You need to remember that we compare nominal and substitute. Nominal was by CAD, substitute what CMM made by numeric techniques. So now, okay, numerical techniques, and it was made up of simple geometrical shapes. So the standard ones we talked about, like the plane, line, cylinder, sphere, cone. So these were the standard things. Also, we studied in this that there were two things. One, which was degree of freedom, and second, which was MMNP. Degree of freedom was the mathematical minimum number of points. Like for line, it was 2, for plane, it was 3, for circle, it's 3, for sphere, it's 4. So these were the mathematical minimum number of points. But then I discussed that as those points are only mathematical, and as CMM is dealing with the real life scenario, so it needs some more info other than these degree of freedoms or the minimum number of things. Now, we also talked about that it can be infinite, but then after certain number, which was determined by experiments, we reached to a conclusion that yes, like for suppose line, uh, 2 points are mathematically sufficient to define that line. But to plot it by CMM, we need minimum 3 points. Now, of course, if there are four, well and good. If there are 20, very nice. But yes, 3 points are well enough, and the improvement of accuracy in plotting these lines after 3 points is not so high. So, when the improvement is not so much and effort is very much, then we say, okay, fine. So, this was the uh, saturation point, saturation level, and we said that these are the metrological minimum number of points, and then we decided by experiments. I gave you a chart in which the number of points were fixed. So now we will continue from here. That suppose you have this, our CMM will give you these points, and once if you are having these points, how would you construct the how would you construct the form? So for this, there are some methods, and we will be talking about these methods today. Fine, so we will continue from here, these methods. Now, whatever these methods be, all these things are to be constructed mathematically. All constructions are done mathematically. So, what I will do, we will discuss all the mathematics related to CMM in today's lecture. So, what all can be the different sort of mathematics used? I will tell you. One are different techniques of form fitting. Now, this form, when I say it, it means the same thing. It means the contour of the object form fitting. Then there is something which is the coordinate system. Now you must be knowing coordinate system. I'm pretty much sure, and don't think that this is something what you already know. We will not be talking about, not be talking about Cartesian, polar, etc. Spherical, cylindrical. This we will not be talking about. So don't think that okay, fine, I know, and this fellow will again be talking about something which I already know and waste my time. No, it's not like that. Today we'll be talking about machine coordinate system. I will write CS for coordinate system. Excuse me for my laziness. And part coordinate system. And the relation between these two is called as alignment. So we will be today discussing about this, this, and this. Okay. So this is the total scope of today's lecture. Fine. So next thing, the mathematical modeling methods. So there are, I will give you the chart again. It will be quite helpful. Yeah. See, these are some of the algorithms most commonly used, what we often use. First number is least square methods. Second one is min-max method. Third one is hybrid method. Other than this, I will tell you two more, maximum zone and minimum zone. But after this, why I will tell you this? Because uh, there can be n numbers of algorithms, right? But why we are talking about this, specifically only these four things, because these are important and very common. So if any question be posed, it should be from this area. Even in this area, not like the question cannot be framed from these things. I will tell you why, but we will talk about this and I will explain you why and why not. Okay. Okay. By the way, this min-max method is also called Chebyshev. Uh, Yes, Chebyshev. Chebyshev. This is Chebyshev. This part is only pronounced. Okay, don't get confused with TS. And by the way, this is in mathematics also. You will see special functions whenever you will, if and when you will read this as it is proper noun. Sorry. So proper noun can be written by alternate spellings also. So it is also some places written as Chebyshev. Chebyshev. Okay. So fine. So this min-max method is also called Chebyshev. One by one we will see. This is the most important part. This one. If a question in exam will come, it should come from this area for numericals. And these things, theory can come. So talking about this will waste too much of your energy and effort. So we will not be discussing too much of mathematics for this, but I will explain you what and how. This we will solve some questions and practice the methods also. Okay. So now for this method, which is your least square method. I guess you must be knowing this already, but still we will talk about this. So in least square method, what we do, we try to minimize the sum of squares of error. Now what is this error? I will tell you. This is our aim. Fine. And if you be knowing linear algebra nicely, then if you know linear algebra, in linear algebra also, the method of least squares are there. It's just stated like this. Fine. So it's mathematically linear least square is a problem of approximately solving an overdetermined system. This point is there of linear equation ax equal to b, where b is not an element of column space of the matrix A, and the approximate solution is realized by the projection of b onto the column space of A. Now, if this line, if this paragraph, if I have to discuss, then I will have to teach you linear algebra entirely. So, if you see this in book or somewhere, this is correct, but we will not be talking about this too much. Our this line, what I have written over here, minimize, aim is to minimize the sum of squares of error, and this thing are same. Okay, but this can be visualized and understood easily, and this, of course, you need some more of mathematics, nothing else. Okay, so we'll come back to our least square thing. So suppose you have a curve. This is your curve. It, like I have made over here linear. It can be your non-linear also. Okay, and I tell you that here is a point. Okay, so what does it mean? What is the error of this and this curve? So it means like when I was putting the value of x equal to x naught, then I was getting y naught. Means if the equation of this is y is equal to some ax plus b. So when you put x naught in this thing, you will get a value of y naught, which will lie on this yellow colored line. But if someone is telling that no, my value of this y prime, then in this case, what is the error? So error is the difference in expected and obtained. This we call as error. Fine. Similarly over here, if for some x is equal to x naught, you are getting some y naught, and our value of y prime is here. This is not like compulsory that this y prime has to be up. That's why I'm showing over here as below. So this thing is known now as error. This is y is equal to fx. So in least square method, what we will try to do, we will construct an objective function. Aim will be very simple. Aim is to minimize the sum of square of errors. So to do this, we have to construct an objective function. So our objective function will be, suppose, some function of these errors. Then we will square it up. Then we will take the sum and we will try to find minima of this function. Once if you are finding this, our aim is done. Our work is finished. Okay. Now we will see the directly by questions because it will be easier for us to understand it. Okay. Now very couple of days back in my group, Gaurav asked this question, and I thought it would be a good thing to discuss it here. Yeah, here's the question. So you can pause the video and try it for yourself. I will be continuing. So, what does the question states? That a straight line is inspected on a coordinate measuring machine. Now, see, this was asked in ESE, I guess, and that time this CMM was not even in syllabus, but they are asking it. So, you don't worry, this coordinate measuring machine, even if you had no idea about this thing, still you can solve this question. How? We will just see. Now it states that a straight edge is inspected on a coordinate measuring machine. It means there was some object like this, and it's like this was the object, okay? And this straight edge was tried to measured by this coordinate measuring by putting probes. Of course, you want as we discussed yesterday, so you can understand this. So this probe touched it to some 3 points. The readings obtained at the interval of 100 mm along the top edge, this was the top edge, are some values. Okay. The straightness error making the end point as reference is dash mm. The straightness error it is talking. So I haven't talked to you, like I haven't told you anything about this straightness error right now. But you know about this error. So how to proceed with this? It means that distance between here to here was 100, from here to here was 100, and this some reading CMM got of this height, maybe not of this height, but some readings it got. Okay, like 100 mm apart, some readings were obtained. So ideally it should be 100 100 100. Like if it is a perfect straight line, no unevenness into this, then everywhere 100 100 and 100 should have come, but it is not coming. So it means that there is some unevenness in this edge and some error they want to measure. Okay, so construct the object. Okay, so we will try to plot the curve. What does it mean? For at 100, at 200 and 300, this length I don't know. Okay, so either you can make it like this. Okay, now when it was at 100, so it obtained some point as 100.1. 100.1. At 200, it saw some 100.5. At last, it saw some 100.4. Somewhere here, right? Here. This height was 100.4. Now they want me to estimate the error, straightness error, making the end point as reference. So what are the end point? This is first point, this is the last point. So construct a straight line. So this is a straight line using first and last point as the reference. And they want me to estimate the error. So estimate of error should be of this point. So on this line, now as we have discussed earlier, this is the error. You know this value. Do you know this value? No. So what we will do? First, we will try to evaluate this point. Then already we will find this height, and that error will be this answer. Okay. So I think you must know. I'm pretty sure you can evaluate this point. You can do this by geometry also. If you want, you can use equations of straight line also. I don't have any trouble, but I will use by plane geometry. Okay. Let this be theta. So this tan theta, you already know what will happen there. Tan theta will be this height, which is 100.4 minus 100.1 by this. This is P, this is B. So this B will be your 300 minus 200. And this should also be equal to this height, which is, I don't know. This is suppose, let this point be Y. Okay. So it is y minus 100.1, this much height, 100.1 by 200 minus 100. From here you can find this y. This y will come to be 100.25. You solve it. As I have solved this, this was asked by Gaurav Goyal. Very nice, good chap. So anyway, so this y you will get. But at this point, what is the value already given of y prime? It was given as 100.5. So what will be your error? It will be 100.5 minus 100.25. So it is your 0.25. This was the answer. So its answer was 100.25. Fine. So I guess now you understood what is the meaning of error. Fine. This was one simple question directly based on the question of error. Now we will talk about further, like one step further. Now you see, now as I was telling you, let's discuss this a little bit more. And this is overkill, but still we will do it. Now to see, measure this straightness. If it would be a straight line, only 2 points was sufficient. But as it is uneven, we took 3 points. These 3 points, as I have told, is MMNP. And if you can see yesterday's lecture again, there was a table in which I have clearly mentioned that for a line, only 3 mmNP are needed for a straight line, straight edge. So they have given only 3 points. Okay, so this question was very practical in fact, but if you will not even know the practicality in so much of detail, still by your aptitude, I'm pretty much sure you can solve it. Okay, but now you can have a better understanding of this. Okay, let's proceed further. Next question is, next question we will take. Question number 2. This question is also, this question, let me see where I have. Okay, let's take a random question. It's not so difficult. Okay, your aim is to fit a curve. Fit a curve passing through points 1, 6, 2, 5, 3, 7, 3, 7, and 4, 10. Fit a curve passing these through using least square method lesson. So you know what you have to do. You have to construct a approximator curve. Okay, how to do this? This I will be doing in too much of detail. Then in next, I will teach you how to do it in short form also. Like the shortcut also I will teach, but the conventional method you should know because that is the basis of it. Okay, so we have to draw it small thing. This drawing, by the way, is not needed still. Like suppose this is the point 1, this is the point 2, this is the point 3, this is the point 4, and this only 4 points are there. 1, some point is 6, then little bit less 5, a little bit above 7, little bit very high 10. So you can pretty much see that it's not a straight line. So but you have to approximate a straight line to it. Like you have to construct a straight line in such a way that the error sum of square of errors be minimum. Okay, so let us assume the equation of this be what you take any straight line equation, it's not a problem. Let us take it to be y is equal to beta 1 plus beta 2x. This is your x, this is your y, and this beta 1 and beta 2 are constant. beta 1 and beta 2 are constant. You know that two orbit points are there. Again, I should not discuss into this into too much detail because you must definitely be knowing y is equal to mx plus c, where this c is intercept, this is slope, but how to do with it. Okay, so this is the equation of this curve. So at this point x1, here will be the y1 and here will be your y1 prime, and you will have to find this error. This is epsilon 1. How to find epsilon 1? Epsilon is y minus beta 1 plus beta 2x. If this is 1, this is 1, this is x1. If this is 2, this is 2, this is 2. These two will not change because these are constant throughout. So better way to write this as this is so on and so goes. So better way to write is like error ith error is equal to ith y component minus beta 1 plus beta 2 x ith component. This is the error. Let us construct our objective function. So our objective function is square of error. So our function is square of error, means summation of yi minus beta 1 plus beta 2 xi whole and this thing as whole square, where I was varying from 1 to 4 and the parameters are beta 1 comma beta 2. Fine. So what do you mean by this? That we are constructing a function, and this function are having two separate variables beta 1 and beta 2, and we have to find such values of beta and beta 2s that this error, this function, and this function is the square of the error. This is epsilon I. So this square of this becomes minimum. That is your objective. You have to find values of beta 1 and beta 2 such that f beta 1 comma beta 2 is minimum. Fine. So how to do this? Again, we will put different values of this and we will keep on squaring. Okay, let's do it. So I will write down f of beta 1 comma beta 2 is equal to, it will come, you can evaluate and check, it will come 4 beta 1 square. Okay, let me write it in detail, otherwise some of you might get confused. Fine, so this will be equal to 6 minus beta 1 plus beta 2 into x1. X1 is your 1 only, this whole square, plus second one will be your 5 minus beta 1 plus 2 beta 2 whole square, plus your third coordinate was 7 minus beta 1 plus 3 beta 2 whole square, plus last coordinate yth was 10 minus beta 1 plus beta 2 and x was I think 4 and then square of it. Okay, now you simplify this entirely, it will come 4 beta 1 square plus 30 beta 2 square plus 20 beta 1 beta 2 minus 56 beta 1 minus 144 beta 2 plus 210. So this is our big objective function. This is our objective function, and you have to minimize this. Now, as there are two variables, beta 1 and beta 2, so how to do that? You have to differentiate this with once with beta 1 equated to 0. This will be your equation 1. Then differentiate partially with beta 2 equated to 0. This will be equation 2. From here you will have two equations in beta 1 and beta 2. You have to solve them and get beta 1 and beta 2. And this value, when you will put in equation 1, your equation is this. This is your equation 1. Then you will get the equation of line. Okay, let's do it. So when you will do this thing, you will get an equation 8 beta 1 plus 20 beta 2 minus 56 equal to 0. This is your first equation. And your second equation, I'm just differentiating it partially. I'm not doing anything very big over here. You can, pretty sure you can do it better than me. Then it's 20 beta 2, sorry, 20 beta 1 plus 60 beta 2 minus 144 equal to 0. Now you have two equations in beta 1, beta 2, solve them. Solve these two. You will get a solution as beta 1 to be as 3.5 and beta 2 as 1.4. And put this in equation 1. So your equation is y is equal to 3.5x plus 1. Sorry, beta, our y equation 1 was y is equal to beta 1 plus beta 2x. So our equation will be y is equal to beta 1 3.5 plus 1.4x. So this is our answer. So this is the line which will have minimum errors. Okay. So if you will plot this line, sorry, John asked me to write neatly. I'm extremely sorry. My handwriting is not so like good, man. But still, y is equal to beta 1, which is 3.5 plus 1.4x. This is your answer. For this curve, for this straight line, your errors will be minimum. So this was the entire method. So what I'm doing, you have to see this, that as is for the method, what I did, this was our question. We assumed the equation, we found the errors, we constructed an objective function, then then this became a question of calculus where two variables were there and our aim was to minimize this. Then we minimized it and found the equation by putting these values back into the equation number 1. Okay, so this was one thing. But do you think such idiotic type of methodology will help us in any sort of examination? No. If if a question is asked in the exam and this is the way you will do, you will definitely be leaving it's better to leave the question. So this entire method was very not so logical. I will not say logical. I would say it is not very economical. So we will stick to some easier way. And this easier way we will get by some another method. I will tell you what. See, If you see, like if you observe that our objective function, which was of beta 1 and beta 2, was of something of this sort, yi minus beta 1 plus beta 2x square. Differentiated now. Let's see what happens. Let del alpha del beta 1. It will come as summation yi 2 will come here minus beta 1 plus beta 2 x into beta 1 as minus 1. Okay, this equal to 0, and differentiated next time with del beta 2. So this will come as summation 2 yi minus beta 1 plus beta 2x, and when you will differentiate this again by beta 2, then this will become 0 and this will become as minus x equal to 0. Let this equation be 1, this equation be 2. Okay, now let's open these equation 1 and 2 and see further. So as equated with 0 on right side, this 2 and minus 1 will get cancelled. You can divide it and get rid of this and this negative sign can get rid of it. So see, first equation, what is becoming? See, first equation 1a I am writing, it is becoming summation yi minus summation beta 1 minus summation beta 2x equal to 0. And second equation 2a, I will write it is summation x yi minus summation x beta 1 minus summation x square beta 2 is equal to 0. Take negative sides on the right side. It is becoming summation yi is equal to summation, see, as beta is common, you will take it out, beta 1 outside, and this summation is going for I is equal to 1 to 4 in above case, but let us take till n. Okay, so this 1 to n, so here is 1 which will go to n plus beta 2 is common, summation x 1 to n xi, and our another equation is becoming x yi summation 1 to n is equal to, again, beta 1 is common, xi, here I have missed the I. Okay, x here also xi plus beta 2 summation xi square 1 to n. Okay, now these two equations are called reduced equations, and in all our further problems we will be using these set of these two reduced equations. Now there are a few things to note, that in this particular question our number of unknowns were only 2, so we got 2 set of reduced equations. Fine. So suppose if above equation I will solve this above equation again. So our question was that we'll write it down. When x was 1, our y was 6. When x was 2, y was 5. When x was 3, our y was 7. And when x was 4, our y was 10. And you were asked to construct a line using this data. So what you assumed? You assumed the equation of curve method 2. Method 2, and this is the method what we will always stick to. So we assumed the equation y is equal to beta 1 plus beta 2x. Fine. Now we have to directly write reduced equations from this. How to write that? How many unknowns are there? 2. Beta 1 and beta 2. So you will have to write two equations. First one will be summation. You take summation over this. So it's summation yi equal to beta 1 summation of 1 plus beta 2 summation x. Now this summation will go from 1 to, how many points are there? 1, 2, 3, 4. So 1 to 4. 1 to 4. 1 to 4. And second will be multiply the above equation with x throughout. So it will be summation xi yi is equal to beta 1 summation xi plus beta 2 summation xi square from 1 to 4, 1 to 4 and 1 to 4. Now we will take the values. These are okay. What all you have to find? Summation of x. So summation of xi will be 3, 6, 10. This will be 11, 18, 28. Second thing is coming xi yi. So xi yi will be 1 into 6, 6, 2 into 5, 10, 3 into 7, 21, 4 into 10, 40, and one more thing is there which is xi square. So square this xi square. So 1 to 1, 2 to 4, 3 to 9, 4 to 16. Sum it up. 16, 16 and 20, 36, 37, 77 I think. So, okay. 5, 5, 9, 14, and 14 and 6, 20, 30. Okay. Now the equations are summation yi, summation yi 28. 28 is equal to beta 1, beta 1. This 1 is summed 4 times. So it is 1 plus 1 plus 1 4 times. 1 plus 1 plus 1. So plus 1 plus 1. So this is equal to 4 only. Like summation of 1 for 1 to n is equal to n. If you remember this, then it will be easy. So this is 4 plus beta 2 xi, beta 2 xi, 10 beta 2, 10. Second thing will be this one xi y, xi y 77. 77 is equal to beta 1 xi, beta 1 10 plus beta 2 xi square 30 beta 2. Solve for beta 1 and beta 2 from these things. You will again end up getting the same thing. Okay, solve them. You will get beta 1 as 3.5 and beta 2 as 1.4. You will get the same values. So this method is quick, because for explaining you it might have took some time, but in even if in exam it is coming, drawing this table side like is very simple, and these three things you can do very quickly. Solve these two equations by calculator, get the answer, get rid of it. Okay, so we will, all our further questions we will be solving by this reduced method only. That above conventional method we will not stick so much. Okay, now second thing is that, now come back to our original thing. So as per our original chart, this chart what I have shown you earlier also, that there is something called as linear least square methods, linear least square method, something which is also called as non-linear. So this we have seen above, we saw above. Now non-linear least square method means, so the equation will be like, it can be parabolic also, it can be exponential also, so it varies, like from question to question it varies. Suppose in the above question only, where our values of x and y was like such a way, like our x and y, I'll write down again, x and y, when x was 1, 2, 3 and 4, and our y was 6, 5, 7 and 10. Someone will ask me to fit another type of curve, fit another curve which is parabolic of form y is equal to ax square. This is the question. So how to do this? Now a very smart method is by the same conventional method. Conventional method will be to find the error. Error will be yi minus axi whole square. And then we will directly sum it up, square it up first, square of error. So yi minus axi square whole square. So this is a function of only one variable a. So let this be function of f of epsilon, f of a. So del f by del a is equal to 2 yi minus axi square into minus x square. This we have to make equal to 0. Now as you know that it is equal to 0, so we can, this thing we can ignore, and it's become, and this is summation, right? This becomes summation of xi square y minus axi4 equal to 0. And this value of this summation of x square y and this you can get from our table, this table which I have shown you earlier, and then putting the values, there will be one equation of a, and on solving you will get a as 0.703. This will be your answer. So the same logic can be used for non-linear models also. Okay. Now there can be question where you can reduce this non-linear form into this linear thing. That also you'll see one example. Now type 3 we are seeing. Type 3 is some non-linear which can be reduced to linear form. Example. Suppose you need to fit a curve of type y is equal to a exponential bx. Okay. Now this is the best function I can think about, which is very much non-linear. Okay. So you have to fit this. So now observation is, first it is nonlinear. And how to fit this? Of course, you know the method. I have already told you that you find the error, then square it, take the maxima minima, and you solve it. No issues. That is perfectly fine, as we have solved just above the question, just above it, right? But there is another way also, and I want to discuss that also. Okay. What I will do in this, I will take ln, taking natural log both sides. And this is by the way called ln. Okay, so it will become ln y is equal to ln a plus bx. Okay, I have used the property that ln of e is equal to 1 and ln is equal to log base e. This is only for natural log. Okay, so I have took ln both sides, no issues to this. Now, what are the variables into it's called a variable. So variables are this thing, entire thing, and this b. So variables are ln a and b. Number of variables are 2. So you need two equations to solve this value. What I will do, I will assume, I will say let ln y is equal to capital Y and x is equal to capital X. Then our above equation will become, and this ln a is equal to beta 1 and b is equal to beta 2. We are assuming it. Any problem into this? No. Assume. Putting these values into this, what you will get? You will get capital Y is equal to ln a is beta 1 plus b is beta 2 and x is capital X. Now, if there are coordinates of x and y given, can you find y? Yes, you can put ln y into this. Can you find capital X? Yes, they are directly equal to x. So, if these values are known, these values are known, isn't this question reduced to the same format of equation 1 or the type of question what we have solved earlier? We will again write reduced equations for them and solve them. So it means you can simplify some non-linear expressions into the linear by smart choice of functions. So the conclusion from this discussion is, by smart choice, non-linear equations can be simplified to linear ones. Fine. So I can help you with some standard strategy. Okay, some standard tables, like some standard smart choices I can help you with. These are some. Okay. So it has to be clearly visible to you. PDS of this, don't worry, I will put in group. But for discussion's sake, I need to do this otherwise. So see, if your function is of this sort, then you can always take y is equal to y, x square as capital X, and then again it will reduce to this format. And then again from here you will write your reduced equations and solve them further. If this is the format, then you will take this as x. Okay. Now I think this table will be self-sufficient, like self-explanatory to you. Don't worry about too much into this. You can understand it, right? That like suppose if this is the curve what you want to fit, then you will take log, it will become like this, and then you will take this function as capital Y, this function as capital X, and this entire thing we will take one constant which is a, and this is again similar to the linear thing what we have understood. Okay, so let's solve one question from this. So let's try to solve a question. The question be, oh, let me give you this as homework, that if x and y have some values, please try it yourself, means it is not so difficult. When x is 1 2 3 4 5 6 and y values are 7.209, this value is 5.265, this value is 3.846, when x equivalent is 2.809, when 5 it's 2.052, and this is 1.499. Here. Okay, so you fit the curve y is equal to a e to the power px to this, and its equation answer will be y is equal to 9.868 e to the power minus 0.314 is your answer. Please try and check. If you can solve it, you pretty much understood the concept. Okay, so till now what we have seen, again I will bring the same chart back, because from that chart reference only we are seeing what all we have to study. Okay, just a minute guys. Yeah, so this is the one. See, yeah, so we right now we are studying this least square method I have discussed. Non-linear, how you can express into linear, you understood. Now this, what are these parameter least square method? These parameter least squares are for surfaces. Till now, whatever we have studied are for your lines or for some 2D curves. These two methods are for 2D curves. But the same principle of least square can also be used for surfaces. Now, to express a surface, what we do in general, we represent surfaces by parameters, and those parameters can be optimized. Like those parameters are the variable, and that function can be differentiated with respect to those parameters and optimized to suit the coordinates what are given to us. Fine. So this is just more calculation of above thing. So conceptually there is no improvement into this. So asking a question from this area will just take more of sweat, but no such intellectual addition into it. Okay. So we will not be discussing too much into detail into this or any questions from this area because conceptually there is nothing. If these two things you know, then it's well and good. This also you can solve. It's just like using the same least square principle or finding the maxima minima with respect to these parameters. Okay. Now something is called as vague least square methods also. Now what are these vague least square method? Is that suppose you are able to uh, vague least square method. In this, what happened? WIGH, I think GHT, something here. Vague spelling. You please check mine. Okay, I will also see from here. Yeah, HTD. WIGHTD, vague least square method. So in this, what happens? We attach some weights. We attach some weights. Now, what are these weights? These are some additional importance. What happens to it? Suppose there is a curve and you are somehow able to take more information in this particular zone. You were more confident. You were more confident in this data, but you are not so much confident in this zone because of so many reasons. Suppose there is an intricate casting. Okay, this is a very intricate casting. Suppose some casting is there, inside there are veins, and your CMM, what you have done, you have put your CMM probes. From outside, you can take all the parameters, all the measurements very nicely. But inside, how will you take? You will not be sure that even if I'm putting a probe inside, I got a very proper contact or not. I'm not sure. So this is some zone where you are not confident. So what you will do, all the readings, whatever you have obtained, you will feed one, you will tell machine that these informations, these infos are more reliable. Means I trust them. So kindly attach some additional value to it and you will attach some weights to this. So by attaching weights, what happens that you are just morphing the unnecessary data and you are uh, increasing the influence of reliable data. So that is just simple understanding of weights. So if someone is asking what is the importance of this weight least square method, it is to mask the unnecessary or non-reliable data. Okay, it is a concept of weight which has been associated with least square method and has been used to mask out unwanted data or increase the influence of reliable data and to decrease that of less reliable data where least square theory is not changed by using weighting functions. Okay, so conceptually you should understand it is used to add importance. So the most important part from our this is over. This area is done. Because I feel any question, if they will ask, they have to be from this area. Why? You will understand these things. Okay. Now, we will study about this other methodologies, algorithms, which will be Chebyshev. Now, algo number two is your Chebyshev. Chebyshev or min-max. So in Chebyshev or min-max, you have three different things. Okay, as the this suggests. One is your maximum zone method. Don't worry, we will not be discussing these things in too much of detail like what we have done earlier. It is in, this is minimum circumscribed and maximum inscribed. Okay. So the, like in our linear, our main funda was least square. In this, our main funda is something else. In this, what we do, just a minute, I will tell you. Yeah. So in Chebyshev, what we do, we try to minimize the largest distance. Try to minimize the largest distance between two similar shapes. Example, suppose you have one shape and you have very similar shape on this side also. Shape 1 and similar shape 2. So what we do, now as this, suppose this is a plane. So for this, we will take MMNP, which is metrological minimum number of points on one curve. But on another curve, we will take only 1 point, because we will tell machine that, dude, see, these two curves are very similar. So you don't take so much of coordinates over here also. As this and this are similar, you have already took the MMNP on this surface. Try and minimize the distance between them, and on this you take only 1 point. And then machine will automatically construct a surface similar over here. Okay. So on shape 1, MMNPs are taken. On shape 2, only 1 point is taken. Fine. Now, this is the whole funda of this. Fine. Now, it also minimizes the error. Our min-max method. Not many people, this is very wrong nomenclature, but M3 method I will be writing over here. Okay. This is not used in any industries and all. Just for our understanding, we will be using it right now. Okay. So this M3 method, what does it do? It minimizes the error of lower bound plus the error of the upper bound. So this is one thing. Now, this is the principle. Now, there can be no numerical frame from this area. I mean, there can be frame, but if it is coming, it's better to skip. Don't break your head into it. Just know the logic. Then there is something as minimum zone. So in minimum zone, like this minimum zone is actually this thing. See, this minimum zone. Yeah. Sorry, I have written here maximum zone. It should be minimum zone. Okay. So this minimum zone. Yeah. I made a mistake. Anyway, now I corrected it. Okay. So this is your minimum zone. This should be a minimum zone method. So this minimum zone, what does it do? It like its outcome is to minimize the tolerance zone. And like any geometry, where you want to minimize the tolerance zone, then the best method is min-max method, and in that also this minimize minimum zone method. This is the algorithm which will give you the best thing. Okay, and the another one, which is your minimum circumscribed and maximum inscribed. These two are only good for your circle, spheres, cylinders, etc. So if a question is coming, which method or which algorithm is best to measure any circle, sphere, or cylinder, then this minimum circumscribed or maximum inscribed methods are used. Okay. Now the last one, which is the last one in our list, which was hybrid. Yeah. So in hybrid, this tried to reduce the average deviations. This is again good for spheres, and this is also good for spheres. So these two methods are again like no numerical from this area, but someone can ask you where are these hybrid method used. So these are good for your spheres and cylinders because it uses a 4-point sphere fit method. Now they take some 4 points in a cluster and then another 4 points from another cluster, and then they try to fit a circle in that set of cloud points, which I'm not pretty much happy or feel need to teach you right now. These study of these things are very specialized, and until and unless you are doing some research in CMM or into you are not into the construction of it, there is no need to study about it. Okay, so we can skip this thing. Now, other than these methods, there are two more methods which are very commonly used. What are those methods and why those are important? I will tell you, because those are used in manufacturing more commonly. There is something called as maximum contact element and something which is called as minimum contact elements. So in this maximum contact elements, we take the smallest dimension that includes all measured points. I will show you this by diagram, but just let me write first. And this, it takes largest possible element which lies inside the measured point. Let me show you the diagram with this, because these two methods are commonly used for your shaft and holes. It is a very common method to do so. So chances of this being asked is high. Yeah. See, this is your maximum contact element. In this, what we do, we take the smallest dimension. This circle is best or is minimum, which will cover all the points. Like all the points, whatever random points which we have taken, it will be fit well within this curve. Okay. Now this is a very common method used to evaluate dia of a shaft. Okay, this method. So it becomes important. The, the strategy of minimum contact elements. And this one, which is a minimum contact elements, it takes the largest possible element which lies fully inside these data. Now, this circle which has been made, it is fully inside these things. Like these random points which were taken by the CMM, this circle will be the smallest one. And I'm pretty sure you can guess this. It is used to measure the uh, largest dia, largest inside dia of a borehole. This is used. So these were the these were the things which are very commonly used, and that's why I have covered the algorithms. Okay. Now another mathematical things which includes alignment and all, we will take up in next class. Because now I think it's pretty late. I am also running late into something else. So just I will brief you up what we did today. So in mathematical curve strategies, we read one least square method. Then we read about min-max, and then some hybrid. This hybrid was good for your spheres or cylinders. Numerical cannot be asked from this area. Min-max is used for minimizing the tolerance zone and all. And yes, it is also good for your circles and shaft and meeting surfaces. Meeting surfaces. You can use the philosophy of your inscribed and circumscribed thing over here. And least square, this is used for planes by varying the parameters, of course lines and some splines. All these things, splines mean nonlinear things. So all these things are done over here. And if you are very sure about few data, you do the weight. You attach weights to those data. Fine. So now you got an idea. Next time we will talk about the alignment and the coordinate systems related to the machine. Okay. Thank you for them. Thank you for your time. If you are here, kindly like, share, subscribe, increase the curve. Thank you. Jai.